Thank you again for the introduction. Hi everyone. So my name is David Degras, and I'm an associate professor at Boston. I'm on sabbatical this year, and I have the joy and privilege to spend the sabbatical with my team, which is based in CEA in India, with wonderful people. Some of them are here today. So it's been a great year, learning new stuff, being involved in exciting projects, and meeting grants and training. Very happy. I also want to thank DATAIA for the financial support throughout the year. I'm going to get started. I just want to say something. There's a special note presenting here because many years ago my dad was a student at Séminaire and went on to do a career in physics, and so it's nice to be here today. I'm close to it. Okay, so there are two main themes to my presentation today. One is the integration and fusion of data when you have multiple data sources collected on the same subjects and try to find the shared information between those data sources. And the other theme is tensors. And we'll put those two things together. We have experts of tensor decomposition in the room, so that's nice. It's a little impressive. And some of the stuff that we'll talk about, I got the inspiration for this work from some of the papers of researchers that are here today. All right, great. So I'm going to start by giving you some background. I will talk a little bit about chemical correlation analysis. That's the backbone of this work. And then we'll talk about tensors, and then we'll motivate the work that I've been doing for the past few years on this topic. Then we'll get to the nitty-gritty computations. This is a lot of computations. So present some aspects and some methods to solve the problem called tensor multiple canonical correlation analysis, TMCA in short. A lot of the time we'll use those decomposition methods without thinking, what am I doing? What is the stats behind this? And how can I interpret the results of tensor analysis or canonical correlation analysis? I've tried to think about some underlying statistical models that can help understand what we're doing and some statistical guarantees that the sample size grows to infinity. And finally, we'll show some numerical results, some simulations, to show it that it works and how it's working in progress. So I will ask for your forgiveness. Some of it is not published, not worked out in good shape. All right. So I was saying, two things for this work. One is the integration of multiple data sources. I'm very interested in neuroimaging. So imagine you have multiple imaging analyses like on subjects. It could be EEG, electronography, tensor imaging, structural, functional, resonance images. And you might also have some data from Mother Nature, behavioral, psychometric data, demographic data, and so on. So this is one aspect. Another aspect is that nowadays a lot of the data that we collect, that we analyze, have a lot of structure. You might have a tensor structure. So what is a tensor? It's just a tensor is multi-dimensional array. So a vector is a tensor or one, matrix or two, array, tensor or three, and so on. And
seems that there is a problem with the microphone, so I'm just double checking.
Should I get it?
No, it seems that two microphones are open. So people But in
It's
remote
echo.
connection, has some problem to hear what you are saying. Just double checking. Okay. Can you give a try?
Yes. Hello.
Yeah, I think it's clearer now.
Or not?
Okay.
It's good. Why has it disappeared? Yeah. So one claim is that when you have tensors, it's usually a good idea to keep them as tensors when you're going to analyze them and not just vectorize them. That's the claim, and I think pretty much everybody's convinced. I will give some additional arguments for that, but basically there are analytical reasons, statistical reasons, and also computational reasons. So a little reminder on canonical correlation analysis. This is a very old technique. It was coined in 1936 by Karl Haberling. You have two sets of vector measurements taken on the same subjects. And you're trying to find linear combination of the variables in each set that are maximally correlated across the set. That's PCA. The vectors that define the linear combination, so here A and B, my example, are called canonical weights. I might sometimes call them factor loadings, because it has to do with factor analysis, so we'll use either expression. When the newly defined variables are called canonical scores, canonical variance, and the correlation that you're trying to maximize is called canonical correlation. So this is the setup is the theoretical version. We have random variables. You have some actual data. The empirical version is this. And eventually, to try to find those linear combination of the variables that are maximally correlated, that amounts to calculating the cross covariance of your two sets of data, X and Y, and then you do a single value decomposition. So when you do a canonical correlation analysis, you first need to whiten somehow your X and your Y data set, and then do the cross correlation of that, and do the S and B. That will give you the canonical vectors. Okay, so that's standard CCA. So a bit about the history of CCA. So as I was saying, it was the first paper was published in 1936. Since then, there have been a lot of developments and extensions of CCA. First, in the direction of handling multiple data sets and not just two. And a lot of the impetus for the developments came from chemistry, chemometrics, and psychometrics. A lot of work in that area in the 60s and 70s. Later on, as in many statistical methods, we realized that just having some kind of looking for linear features and linear combinations might be a little too restrictive. We want to try to capture some nonlinear feature in the data. And so one easy way to do that is to use some cardinals. And there's some straightforward extensions. And then you might be working with high-dimensional data, in which case you want to analyze the CCA and maybe some sparsity assumptions and penalties. You can also crank up the CCA with deep learning tools. And more directly to today's point, when we have both multiple data sets and with the tensor structure, this is called several things. One word is one expression is multi-way generalized CCA. All those papers are published by people in this room. So, like I was saying, there's a lot of inspiration that it comes from. Okay, and there are different versions of CCA with tensors. That's another one with some people two tensors to work. All right, so that was for CCA. Applications of CCA in neuroimaging are several. Been used as a denoising tool and also as a tool to use multimodal. Here.
And so as a reminder, a tensor is just a multi-dimensional. I'm going to try to keep this presentation a little light on notations and tensor operations and what have you. So this is maybe almost a strict minimum of what. So you have a tensor, it has a certain dimension, or it's called the number of modes or the weights. These are the ways in which you can go through the tensor. The order of the tensor is the number of modes. One key operation to get a tensor is to start from vectors and then do their outer product. That results in a tensor. It's called a rank 1 tensor. So I use this circle as the notation for this outer product operation. The inner product is like a scalar product. Tensors can vectorize them into the usual Euclidean scalar product. And then, of course, we play with tensors and we want to change their shape, either turn the tensor into matrix or the other way around, or vectorize the tensor. So one important operation is called to matricize or to unfold a tensor. And the idea is that your tensor has multiple dimensions. If you want to matricize it in a given mode, you will permute the dimension of the tensor to put the mode of interest in the first position. And then that will become the first dimension of a matrix, and you collapse all the other modes to be just one. And that gives you a matrix. So that's matricization. This is a useful operation to think about tensor products between tensors and matrices. If you start with a tensor X and a matrix A that have compatible dimensions, and you want to multiply them in mode K, what does that mean? You are going to matricize your tensor X in mode K. So now you will have something that's, with my notations, pk by the product of all the other dimensions. And then you will pre-multiply this matricized tensor by the matrix A. And so that can change the dimension of the tensor in that case. And so you end up with a tensor that has the same dimensions as the original one, except in the case mode where you've done the matrix multiplication, you might have changed the dimension. Okay, and maybe one special case of that is if your matrix is a vector, then you can do exactly what I said, pre-multiply by vector transpose, and then you would have one dimension that's going to be 1, and it's not so interesting, so you just drop it. And so if you started from a tensor of order D dimension, you do a tensor vector product. Now your product has dimension D minus 1. And that's pretty much what I need for this presentation. All right, so I talked about tensor. The next thing I want to talk about is decompositions. So the first thing we'll look at is decompositions for just a single tensor. And then we'll move to how to decompose multiple tensors at the same time. I think maybe there it is. So the most common or the best known decomposition for tensors is called the canonical polyadic decomposition. I can't pronounce it. Or canonical decomp or parapack. And basically, you're going to take a tensor and write it as a sum of a number of rank 1 tensors. So remember, rank 1 is an outer product of vectors, and you want the sum. You want to choose as few as possible rank 1 tensors to express your S. So that can be an exact decomposition. A lot of the time in practice, you want to just approximate your tensor. So you can choose the number of rank 1 tensors that you use for this approximation. The problem of figuring out the rank of a tensor, if you think of a matrix, figuring out the rank of a matrix is something that's trivial. But for a tensor for order 3 and more, this becomes a really difficult problem. And there's no algorithm that will find it a finite number of operations and so on and so forth. So a lot of the things that we're used to do with tensors in dimension 2 are, without thinking about it, just become really, really complicated with tensors of order 3 and more. So anyways, the CPD is one way to decompose a tensor. We can extend that and say, instead of decomposing a tensor with rank 1 tensors, we can use tensors that have a higher rank. And by higher rank, I mean multilinear rank. I don't really want to go into the detail of that, but basically that will give you a little more flexibility in the decomposition. And it will allow you to capture interactions between different modes. So that's called a block term decomposition. And if I was to set my multilinear rank here to 1, 1, 1, then I fall back to this CPD decomposition. So this is a generalization of this. And the other very well-known decomposition for tensors is called Tucker decomposition, in which you will start from a tensor X and then decompose it into a core tensor that is of lower dimensions, and that you multiply in each mode by some factor matrix. So these are called factor matrices. To get some interesting decompositions of this form, you might want to impose some constraints either on the factor matrices or on the core. So for example, if you say, I want my core to be diagonal, so only have non-zero coefficients on the diagonal of that tensor, you get the CPD decomposition. So you can think of CPD as a special case of Tucker with a diagonal core. Or if you say, I want those factor matrices to be orthogonal, then you get what is called a higher order single value decomposition, and that generalizes SVD to higher dimensions. The thing with tensors is that you can get a diagonal core if you want to. You can get orthogonal factor matrices. You cannot get both at the same time. Unlike matrices. Matrices, you can do a SVD, and you will have a diagonal matrix, which will be your core with single values. You will have your left and right singular vectors. Everything works well. Doesn't quite work that way, that nicely. Okay, so this is an illustration of tensor decomposition. Here at the bottom, we have the CP decomposition. So these are rank 1 tensors. And this is a Tucker decomposition where we start from our X. We have this lower dimensional core, and we multiply it in each mode by matrices of lower dimension A. By the way, feel free to interrupt me with if you have any questions at any time, please. Okay, so I'm coming to what I'm be talking about mainly today. This is looking at decomposing tensors, but not one at a time, but several, and having a joint decomposition. And the tool that I'll be using and talking about today is TMCCA, so Tensor Multiple Canonical Correlation. So we start from M tensors that are measured over the same n subjects or cases. The cool thing is that the tensors, they don't have to have the same size, the same dimension. They might have different dimensions. And the method handles it smoothly. So I will use the index I for denoting a data set. We will have M data set, so I goes from 1 to M, and N for the subjects, and the index for the subject is T, so T will go from 1 to N. Okay, so to generalize CC to multiple data sets and multiple and tensor data sets, what we're going to do is to look at all the pairs of data sets. We can put some weight on the different pairs. If I'm not interested in a pair, I can set this weight to 0, and it will not enter the objective. For example, if I want to just look at proper pairs, and I don't really care about the variance within a data set, then all those diagonals, I could set them to 0. Or if I have different modalities of data, and I don't really care for one particular interaction between a pair, same thing, I can set it to 0. And then what we have here is, if you will, the scalar product between, or the inner product between the tensors. So these are the data for the teeth subject, ith data set. And I take the scalar product with this rank 1 tensor, which is a direction that I'm looking for, so as to maximize this this product of scalar products for each pair. So I have my x's, and what I'm trying to find is those round v's, which are rank 1 tensors, and I have m of those. Okay, that's the name of the game. So as I was saying, those v's here, I can call them canonical weights, factor loadings, and those scores here, canonical scores or factors. So far, so good? All right, so this problem will not have a solution if I do not put constraints on the variables. So sort of natural constraints would be, and say that I want my tensors to have norm 1, in which case what you'll be doing is to maximize the sum of covariances in pairs of data sets. You can generalize that and say, okay, I don't want norm 1 for each data set, but just on average. That gives something much more flexible that could possibly give more importance to some data sets, less to others. So it will go both to the data. It's not democratic in the sense of giving equal weight to each data set, but it can really go to where the variations are, or the covariations are the strongest. So this is a little more flexible than that. And finally, if you want to maximize the sum of correlations rather than covariances, then you can put some variance constraints on the scores, and basically maximizing the covariance subject to variance equal 1. This is effectively maximizing the correlation. So we'll be working with those 3 types of constraints, mostly the first one and the last one. So our contribution to the analysis of TMCCA is to provide some tools for extending the multiple canonical correlations. So when we work with vectors, to extend it to the tensor framework and tensors of arbitrary order. So we provide some new computational methods for that. We provide a statistical framework for understanding what we're doing in TMCCA and what statistical properties we can expect. There's some little technical things about orthogonality with tensors that are straightforward with vectors and matrices, and when you work with tensors that get a little bit more challenging. I'm thinking of, okay, I've calculated one set of canonical components. What if I want more? Well, then I will put some orthogonality constraints on the next ones. And what you typically do in CCA is that you can do deflation. So you will remove whatever components you found, project the data on the orthogonal of those directions that you found before, and just restart, restart the program. Turns out you have to be careful about how you do that with tensors. It's not so straightforward. And last but not least, we have a beautiful R package. It's called Tensor MCCA. It does everything. It gives some initialization functions. It has different algorithms for solving the TMCCA problem with all the scaling and orthogonality constraints that I've presented to you. And what else? It also has tools for selecting the number of canonical components that you will that are statistically significant, and it has also some bootstrap features for inferring the model parameters. Okay, so that's what I'll be talking about. Before jumping into Tensor MCCA, you might ask, okay, why Tensor MCCA? Why the need for that? Because, as I said, you could just vectorize our data and just do regular MCCA for vectors. That might be very costly to vectorize data because you will not be looking just at a vector of data, but the covariance of it. So if you have something that's 10 by 10 by 10, if you vectorize it, it becomes, I can't count, that's 1,000. And then the covariance would be 1,000 by 1,000. It starts to be big. Of course, it can get much bigger than that. The advantage of working with tensors is that those dimensions, rather than multiplying, they add. So if I have a 10 by 10 by 10 image, then the number of parameters I need to estimate in a tensor MCCA would be 10 plus 10 plus 10. Okay, so I have 30 parameters and not 1,000. That makes a big difference. It makes a big difference in terms of computation, but also if I'm talking about model specification. Underlying the idea of tensor is that there's a sort of separability across the different modes of your tensor. If this is true, so for example, let's say I have EG data and I have some one-dimensional will be the channel, so I think of it as space, one-dimensional will be time, one-dimensional will be frequency. If I can characterize the variations, not perfectly, but quite well, separately in each of those dimensions, then the tensor approach is bigger. And if that was not the case, I could look at tensors that have a higher rank. I was showing some things with block term decompositions, then that could work a little better. This is actually what some of the researchers in the room have been doing recently. But so if your assumption of separability of the different modes is reasonable, then you will get much better accuracy in using the tensor framework. And then just, if you have 30 parameters each in one separate direction rather than 1,000, this makes for much more interpretable kind of models and inputs. So that's the motivation for working with tensors rather than vectors. And yet another thing before I jump into TMCCA, I just want to say that there are tons of other joint tensor decomposition methods out there. So TMCCA is one, but I want to touch briefly on others. One is called decouple CPD. So we talk first about the canonical polyadic decomposition for a single tensor. We can sort of use the same idea for multiple tensors. And the idea is that we have some tensors xi, so we have m of those, and we'll approximate those tensors with rank 1 tensors, some of our rank 1 tensors. This is a part that is dataset specific. It belongs to each dataset. And this last part here is a common score, common canonical scores, if you will, that are common across all the datasets. So this is the agent of the coupling. Right? This is sort of the shared variation, and this is the directions of variation that are different for each dataset. So we're trying to minimize this over those tensor vi L, which are rank 1. Here, L, the index is just to go through the different components, from the first one to the last one, which is the part. As before, we can extend that or relax this requirement of rank 1 tensor. We can take them tensors of higher rank, and this will be the coupled block term decomposition. Yet another way to think of a decomposition is to look at directions, VI, but then we're going to multiply them all across all the different tensors. So instead of looking at pairs, we take our M tensors or M datasets and we multiply the scores, and we try to maximize the average of those products. So this is called Tensor CCA. And the last one is from Fabien, who's here, and of course his team, advisors. So this is a recent paper. I just became aware of it not long ago, so I can't speak much to it. But this is sort of the same family of problems that the one that I'm talking about today. It's a little more general. There's a function G here that can be not the identity, but it's sort of the same family. Here, again, there's a rank R constraint. I'm working with rank 1 constraint, and there's some things related to the scaling that are treated a little differently in their approach. Okay, so with that, I wanted to paint a little bit of a landscape of the different methods for joint tensor decompositions. I've shown 4. I mean, there are many, but these are some of the most most widely used. So now we'll talk about TMCCA. So let me just go back to the problem that we're looking at. This here. So this is a problem that is linear in each of the VIs. Okay, so it's multilinear, but it's not linear in general. It's also it's convex, but the domain over which you're optimizing. So these are rank 1 tensors, so this is definitely not convex. And also you put, for example, a norm constraint. So again, this is not convex. We can bring ourselves back to something convex for the rank 1 constraints and the norm constraints, but the objective itself is not convex. So this is not reducible to a convex problem, the optimization. So what does it mean? It means that we are going to optimize something and end up, best case scenario, at a locally optimal solution, but not a global solution. One thing that I saw pretty quickly is that it's rather than working with a rank 1 tensor, it's easier to work with the vectors that make up this rank 1 tensor. And then we're back to R to RD or something. So rather than working with this, I'm working with the representatives here, the vector representatives. And so we've been looking at 2 different approaches. One, which is called block coordinate descent, in which you will update those vectors one at a time. So this is a 1 data set, so I can go through the different dimensions or modes of that data set and update those vectors one at a time, and then go through the modes and go through the data sets. And there's another approach, which is more synthetic, that will move all the blocks VIK at the same time, and it's called Riemannian gradient descent. So I'll say a few words about both approaches. Block coordinate descent, the idea is to take all our vectors VIK and somehow chunk them up into blocks, and fix all the blocks except one and optimize that block, and then we'll cycle through the blocks and we'll keep improving the objective until we control. And so when we use some norm constraints, if I say I want the norm, my rank 1 tensor VI to be 1, or if I use some variance constraints, then the natural block is the VIKs themselves. If we're looking at the global norm constraints, so that I was saying that on average, the squared norm of my tensors is 1, then we can look at take 1 block per data set and update simultaneously. And so to tell you just a few words about the type of optimization problems that we're dealing with, there's really 3 different types of problems. This first one here is maximizing the quadratic form of a sphere. The second one is a just typical eigenvalue decomposition. And the last one is a linear problem with some kind of well, elliptical constraint. It has a closed form solution. So I will dwell a little bit on that first one, which is maybe the most interesting. And what I'm doing is that I'm rewriting the objective function that we had in this quadratic form. So we're starting, if you recall, by the scalar product between the xit and the tensor vi. And if we vectorize, if we matricize xit in the kth mode, we can say that this inner product that we had was VIK transpose, or the inner product between VIK and my my tensor xit that I'm multiplying all the modes except the kth one by the vector components of my original ground VI. So basically, my inner product between xit and vi, I split it into a tensor product, a tensor vector product in all the modes but k, and then the last one here is multiplying. So I'm doing this on one side. I'm doing this the same on the other side. So this is a matrix. Okay, so I put a term here, and then I do the same idea for all the other terms in the objective function. So that would be the sum for the j's other data set than I, and I can write things like that. And so this is my term B that I have. So I have my A and my B, this guy and this guy. Okay? And I have this constraint here, so we can just rework or change our variable, and we arrive at the problem that we had in the previous slide. Okay, so we're trying to maximize a quadratic form on a sphere. This is pretty old. People have been working on that in the 60s, maybe even before. When you do, for example, you have optimization problems where you build locally a quadratic approximation to an objective, and you have some kind of sphere, or you don't want to go too far away from the current solution, you will try to maximize or minimize this quadratic within the bounded region. This is called the trust region problem. So this is what it is basically. But I'm not looking at the inside of the region. I'm just looking at the surface of the sphere. And well, you can show that it's pretty easy to see that if you have this constraint, norm of x squared is equal to 1, then I can add a multiple of the identity matrix. This will give me lambda times norm of x squared. So this is just lambda, so it doesn't change anything to the problem. The cool thing, though, is that if you take lambda big enough, then this whole matrix becomes strictly convex, and so you have a convex objective. And then if you drop this constraint just for a moment, you have a convex problem. You can find the solution in closed form depending on this lambda. And it's known that there's a single lambda such that the norm of this x of lambda is 1. Or in other words, if I write this function here, the difference between the square norm and 1 is 0. And it turns out that this square norm is very easy to write. It's a rational function, and the delta i's here are the eigenvalues of A, and this thing here depends both on the B and also those eigenvalues. So to figure out the right lambda, the one that cancels this function g, we're trying to find the root of a rational function. It has the good taste of being decreasing. So it's really, really easy. It's a fraction of a second to do computationally. So once you've found the lambda, then you can get back to the x of lambda and you get the solution. It's very, very quick. Okay, so that's the main problem for the VCA, for the block coordinate descent. So now I'm switching to the other method, which is the remaining gradient descent. So the idea will be to calculate the gradient of the objective function at our current solution. I'll call it nabla f of e halves. And then we want to take a step not exactly in the direction of the gradient, but make sure that we respect the constraints that we have. So the scaling constraints and also mostly the scaling constraints. And so to do that, we can project our gradient on the orthogonal of the gradient of the scaling constraints, and that will make sure that we remain approximately, we satisfy approximately the scaling constraints. So I call this direction H. And so that will give me the direction of in which I will take my step. And to make sure that we respect strictly the scaling constraints, we need to do something that's called retraction. And the retraction, one way to do that is to just rescale the solution. So I take my current solution, b hat ik, this data set, kth mode. I will take a step in that direction, and to make sure that I still have the unit norm, I divide by itself, by its norm. Okay? And so this guy has norm 1. So now the problem is to find the best step size for your gradient step. So this alpha here. This is one strategy. The other strategy is to use some idea of rotation. And so if we scale the search direction h by k, then we can take a linear combination between our current solution and this. And if I put the right coefficient, so cos of an angle, the sine of another of the same angle, take the square norm, you still get what you want, 1. And so now the problem is to find the best data, best rotation. These ideas are not mine. They're found them in a great book by Nicolas Boumal, 2023 book about manifold optimization. I highly recommend this book if you're curious about manifolds and optimization. So these are the main ingredients of the gradients, the remaining gradients. Okay, so you have the two main methods. I want to say a quick word about how to obtain higher order canonical components. So let's say we solved the problem once, and we want maybe more than one canonical component, typically do. So how do we find the next ones? Typically, we impose some orthogonality constraints on the next components, and those constraints, they can pertain either to the, if you will, the canonical tensors VI or their vector components, or we could put constraints on the scores. And it's kind of up to us to choose depending on what we want to do, the meaning we want to assign to the analysis results. And I don't want to spend too much time on those constraints, but I just want to say that in some cases, you can do the standard thing, which is to deflate the data in a suitable way and just pass on the orthogonality constraints from the optimization variables to the data, and everything works smoothly. That's wonderful. There are some situations with tensor where you cannot do that, and you need to keep those orthogonality constraints explicit. So very quick example. If I put some orthogonality constraints on my canonical tensors, my weights, you could think of doing a deflation after finding first L minus 1 components. I can remove their contribution from the data and get a new data set and just restart the CCA without any orthogonal constraints. That's a bad idea. That's not the right way to do it. And the philosophical reason is that you're doing some kind of projection of a rank 1 of a rank 1 solution, this VI here, on a subspace, but the projection of a rank 1 tensor in a subspace is typically not rank 1. It does not preserve the rank 1 property. So you cannot do this kind of thing here. You cannot pass the projection from VI to the data this way. What you can do is to use this idea of projection, but in one given mode. So you're going to matricize your xi or xit, and then project on the orthogonal of a previous solution, but just in one mode. You choose which one. And then you will get some automatically the solution that you will find when applied to the deflated data will satisfy the orthogonality constraint. So things work nicely. The big question is how you choose the modes. You might have some analytic reasons for choosing this and that mode. I want, my canonical vectors to be orthogonal in the first mode or second. But if you don't have any favored modes or something that's more interpretable than another, then you might try just all the different modes to find whichever gives you the best canonical score. There are some ways to avoid that, actually, and I'm not going to spend too much time on it, but if you put some constraints not on those tensors, but on the scores, in the canonical scores, and you say, I want my canonical scores to be orthogonal to each other, and then you avoid that problem. So that's one way to avoid the problem. Speaking of constraints on the scores, so we have this kind of constraints. They are equivalent to this. So now I have my rank 1 tensor that needs to be orthogonal to general order or general rank tensor. Sadly, this type of constraints cannot be passed to the data. So you are forced to keep it in the optimization. Okay, let's see, how am I doing on time? Oh, okay. All right, so we have some results of numerical convergence. This is kind of standard fare in terms of the results and the way to prove them. Looking at the BCA, you can show that, of course, this is an algorithm that increases the objective function at each iteration. So the sequence of objective values will be non-decreasing converge. And then the sequence itself has accumulation points, which are blockwise optimal solution. BCA optimizes one block at a time, so you can only hope to get blockwise optimal solution. And under additional constraints, you can show that the sequence will either converge to blockwise optimal solution or to continue of such solutions. Okay, and so one important contribution of this work is returning to statistics. Try to understand if there's an underlying statistical model to justify or to understand what we're estimating when we're doing tensor MCT. And it turns out that there's a factor model, which is this model, in which you're trying to recover those factor loadings here, and also the factor scores. And this model, the TMCC can consistently recover all those model parameters. So you have some consistency results, you have some square root and convergence. You can prove some asymptotic normality results for the estimators of the factor loadings, and also for other parameters. Okay, and so with that, I'm going to switch to the last part, which is just some numerical experimentations. So here I'm simulating a simple model, 3 datasets, 4 factors, and what's happening here? A bunch of stuff. What is important is that I will vary the sample size. And what I want to show you is first, on one dataset, I'm looking at a mean squared error in the estimation of a factor loading for the first dataset. And here, this is a log scale, so you see here the root and convergence consistency. Here we have the tensor CCA. So each line is one component, so you have the consistency for the first, second, third, and fourth component. And here we have sort of the same story, but here we have vectorized the data. Same data, but vectorized, and we just do standard MCCA. And you can see by comparing those two things, which are super obvious, but the convergence is lower here. Okay. So if you have the right model, if you know that the tensor model is the right one for analyzing your data, you should definitely not vectorize your data. You do some statistical accuracy and efficiency. And the Meteor simulation that I want to present quickly is a comparison of different methods. The approach that we propose with some initialization and using BCA as the optimization tool. Same thing, but applied to vectorized data. The MGCCA approach of Glo again and colleagues with an SVD initialization, and then the coupled tensor decomposition that was the coupled CPD that I presented at the beginning. So the performance measures are, first, well, how do you do on the task that you set yourself to do? So maximizing the sum of covariances in this case. How do you recover the factor loadings, the canonical weights, the VIL? Same thing, but if you're not looking at the factor loadings one by one, but looking at a space that is spanned, how do you recover that subspace? And lastly, applying TMCCA, we can get some scores, one for each data set, and we can average them to get an estimate for the underlying single common score. So I have a S hat, and I want to look at the correlation between my estimated scores and the true scores of the model. So we implemented that in R, so with the Tensor MCCA package. The RGCCA, which is an old version, fixed a couple of bugs, but I haven't looked really under the hood if it's working as it should. There are more recent versions now that I will try later on, and we also have some custom code for the couple CPD. So just a few pictures. The left here, we're looking at the maximization of the objective function. This is the truth. This is using the true model parameters, and you can see that, as expected, all the methods based on the data fit a little better than the truth. This is the approach of Glogan and colleagues, so I call it MM. This is for minimization, majorization, or the other way around. Forgot. This is our proposed approach. It's slightly better, not by a lot. And this is what happens if you vectorize the data. So you get a much better objective. Of course, because if you vectorize the data, you remove the tensor constraint. You don't have a rank 1 tensor. You have just one big vector that you're trying. So you can only do better. So okay, you do much better, but you pay a price. And the price that you pay is seen in that figure. Because in terms of the quality of the recovery, the true factor loadings, it is the cosine distance between the estimated loadings and the true loadings. So the lower the better here. And that's what you do with after vectorizing the data. Forwards. Yeah, we're doing better. And this is, oh, sorry. That was with the vectorized data. And this is the coupled CPD, the coupled tensor decomposition, which is really based on that model. The CPD is the coupled CPD is really exactly based on that model, and it's doing pretty bad in our simulation. So this was a bit of a surprise. One possible explanation is that it's not using any assumption of orthogonality. Where does the orthogonality reside, in which mode, and so on and so forth. Whereas those methods use the true orthogonality information about the loadings. What is this here? So same story, but now we're looking at the recovery of the space spanned by the factor loadings and not the individual factor loadings. This can be important sometimes because if you have two factor loadings that have a variance that are very close to each other, then in your estimation, it can switch. You can estimate really the one with the highest variance, but it will just have a slightly lower empirical variance in your data. And so there might be a kind of switch in labels, yet you still have the two right loadings just in the wrong order. So looking at space that is spanned by the factor loading collectively sort of prevents against this type of switching. So we have kind of the same story. And finally, we see how do we recover the scores, so they're specific to each subject, the STs. And well, we're close to 1 most of the time. There can be some situations where things go badly, and they can be more or less frequent, depending on the method that you're using. And again, the coupled CPD is doing pretty badly. So to summarize, the proposed TMCC approach yields the best results for the task at hand. I've shown what happens with maximizing the sum of covariances. You have pretty much the same results when you're maximizing the sum of correlations. The MGCCA is closely behind, and I have to remark that this is a more general method at a function. It can do different types of optimizations that handle different objective functions. So this one is a little more specialized, so maybe it's not so surprising that it does it better. The other takeaway is that if you trust approximately the separability of the decomposition along different modes and vectorize their data. And just to say that we did this type of simulations in different setups. Maximizing some of correlations rather than covariances works kind of the same. And also, one thing that did not really show is that selecting the rank of the decomposition is important, and using permutation tests works really, really well in our situations, in our simulations to recover the correct one. Okay, and so to finish, I've talked about TMCCA method for finding canonical variables that either maximally covary or correlate between multiple tensor data sets or measured on the same subjects. You can use TMCCA either to explore your data. Maybe you have different imaging modalities. You want to see how they speak to each other and what common information they share and in which directions. Or you can use that to extract features for some downstream tasks, such as classification or prediction problems. What I try to emphasize is that working with tensors is different from working with vectors, and then you really need some specific methods and also some specific theory for the methods and models. And one good things about tensors is that the dimensions of the tensor, they add rather than multiply when you vectorize things. And so we have a young but highly optimized R package to implement all those methods. Right. And so one last slide, future directions and progress. I'm working on applying those methods to neuroimaging data, some leads for applications to look at concurrent EEG functional MRI acquisition, and also to try and connect, well, no pun intended, to connect some connectomes. You have some structural connectomes and functional connectomes. So you can think of a connectome as a graph, and a graph is like some sort of matrix, adjacency matrix or weighted matrix. And so this fits very nicely in the tensor framework with at least 2 dimensions for the graph, and then you can have multiple replications or conditions for them. If you have some bright ideas or things that you want to discuss about possible applications, I'm a taker, so please speak to me. And so some low-hanging fruits for this work to integrate different types of constraints on the tensors. If in some cases you want them to be non-negative, this is something that it's not too hard to get. To add some regularization, if say, you have high dimensional data and not enough samples, then you can use L1 or L2 regularization. And if you want to go in the direction of handling nonlinearities, you could use some kind of cardinal approach, and things would work more or less the same. And one thing that I didn't talk about, but the whole CCA machinery is based on the idea of sequentially estimating canonical components. With matrices, this is fine. It doesn't change anything. You can do it simultaneously or sequentially, you'll get the same answer. This is not true with tensors. So from an optimization perspective, it would be better to estimate all the canonical components at the same time. It's a much more hairy problem in terms of optimization. But this is, there are some directions for making that happen. Right, so that are possible. Okay, so this is my work, and also with the help of my graduate students at Chinmin Chu and Yiming Shen, who are at UMass Boston with me. And with that, I thank you for your attention. Happy to take any questions.
So you presented everything in given value space. What was complex data, which is in the imaging?
Great question. I don't see what it would work.
Would you like add another dimension for just training imaginary the sensor, or you work directly in the...
So let's see. So you have your direction. So now you have to have complex part and imaginary part, real part, and then the inner products. I just yeah. Take the norm of that. And then what is in terms of the computation? So you're doing some SVDs and stuff. So yeah, maybe taking whatever direction with the highest highest eigenvalue in terms of norm. I think it should be, yeah, it should extend, but this is something to look at. Yep.
Yeah, of course I have questions. I would start by asking about the kernel extension. How would you mix kernel extensions with like tensor models? Like what would be your approach on that?
Yeah, that's a good point. I'm trying to find some product somewhere. Right. So if we're looking at this, so this is nice in rank 1. So if we had this separability here, that would be great. We could almost apply some tensor in each mode and do a product of those things. But now this guy is of general order. So I think this idea will not fly. So I guess you would have to define a kernel on the tensor space in a way that is tractable. So yeah, I haven't thought about what kind of kernel would work well on a tensor space. That's something. Yeah, that's a good question.
It was just if you had already thought about it, because I tried to think about that, but I don't see how to do it. So
yeah.
Wondering.
Yeah, good question.
David, so you presented two different types of optimizations, according to classes and then.
Yep.
So in your simulation study, did you compare the performance?
Yes. Pretty much the same. The gradient base is a little better, it's slower. And something that was surprising to me, I didn't talk about it, but I spent quite some time looking at the initialization of the algorithms because it's not convex. The answer might depend on where you're starting from. It doesn't make a whole lot of difference. I have some initialization that's based on some higher order SVD works. Something based on doing pairwise CCAs, the standard CCA, after vectorizing the data sets, or taking random points. All in the same ballpark. There's not one that's much better than which is surprising. I thought it might be a different story with a real data set that's much bigger, but in those simulations it didn't make much better. So no matter where it starts from, you kind of recover and arrive at a locally optimal solution. That's also something I didn't really talk about, but give the theoretical guarantee that you can converge close to some blockwise optimal solution. In practice, what I see is that you get your solution, you can check the KKT, the Karach-Tucker equations, make sure that they're verified. But you can go to the second order and calculate a Hessian matrix of your depth signature solution. And then there's a result that says that if you come from directions that are orthogonal to the gradient of the constraints, for those directions, if the Hessian is non-negative definite for those directions, then you have a local maximum. And pretty much every time I check in practice, I do get a local maximum. So not just blockwise optimal, but just local, which is good. So there's always this tension between what we can prove. In theory, that there can be some really pathological cases where we're applying just something blockwise optimal, but in practice, a lot of the time, we find some local happens.
I had a question about the deflation for this course.
Yep.
So you said that yes, we had to keep the new constraints for other vectors, other tensors. So I wondered if you could elaborate a bit on that.
It's been a while. I've looked at how it's done. Let me see if I can remember.
Is it because you have your original space that you assume to be separable, and so you have your tensor constraints, and then when you modify the space by deflating, you want to still have that, so you put the constraints to emphasize that?
I'm sure. So let me tell you what happens. How does this handle is that you can take, same as before, so I'm optimizing the block VIK, eighth mode in ith data set. So I can take, again, the tensor vector product in all dimensions but k and move it here, and then we'll have VIK needs to be orthogonal to something. And so what we're doing is that we're back to this problem. So this is just the correlation. So why do we only have a linear term in the correlation? Because the term in variance, which comes from here, or this guy here, is 1. Set the variance to be 1. So when we're maximizing the correlation, we just have this linear term, which is basically this guy. So we're trying to maximize that. We have this constraint here, plus some orthogonality constraint. And the orthogonality constraint, by change of variable, you can push it here, change A, change W, and then you're back to square root 1. And so it plays nicely.
It was like it was more the reason why you had to consider the constraints.
The reason. So I'm not sure. You need to have some orthogonality constraints. So it can be on the weights or on the scores.
Oh, okay. I think I got. So you don't deflate, but you.
No, I don't deflate. No, I don't deflate. And what I was saying is that when you put the constraints on scores, but if you're trying to maximize a correlation, it's kind of standard to say, I want my scores to be uncorrelated. It also avoids the difficult problem if you're putting some constraints on the weights themselves, then you need to choose in which mode the orthogonality holds. And if you don't have a strong prior reason to choose one mode, then you would have to go through all different modes and figure out which is the best one to put orthogonality on. Doing scores, you don't have that problem. There's a price to pay. If you know that that orthogonal, that your factor loadings are orthogonal, let's say mode 1, but you just say I want orthogonality with respect to scores, you will recover those factor loadings, but the convergence will be slower than if you said explicitly, oh, I know in which mode they are. That works with this price.